Welcome to The Explainer. Today, we're tackling one of the most mind-bending ideas in all of physics, time itself. You know, we all feel it. It feels constant, right? Like a river flowing at the same speed for everyone, everywhere. But what if I told you that's just not true?
So let's just jump right in with a huge question. Is the now that you're experiencing at this very second the same now for someone flying in a jet or for an astronaut zipping around in orbit? Does your watch tick at the exact same rate as theirs?
Well, according to none other than Albert Einstein, the answer is a hard no. The flow of time incredibly depends on how you're moving and even where you are. And look, this isn't just some philosophical thought experiment, it's a real fundamental property of our universe. The name for this crazy effect is time dilation, and what it means, literally, is that for some people, time's clock ticks by slower than it does for others. I know, it sounds like science fiction, but it's real. Okay, let's dive into how this is even possible. So to really get our heads around why time is so flexible, we have to start with the one thing in the entire universe that isn't: the speed of light. Back in 1905, Einstein built his whole theory of relativity on this one unshakable idea, and it has some seriously weird consequences, which a simple thought experiment shows off brilliantly. Okay, just picture a really simple clock. It's just two mirrors, and you've got a little beam of light bouncing between them. When that light hits the top mirror, that's tick, and when it hits the bottom, that's tock. When the clock is just sitting there not moving, the light just goes straight up and down. Easy enough, right? But now, what if that clock is on a super fast train? For you, standing on the platform watching it whiz by, that little pulse of light has to travel farther. It's not just going up and down anymore. It has to travel on a diagonal path to catch up with the mirrors as they move forward. And here's the absolute kicker. This is the whole key. That speed of light has to be the exact same for the person on the train and for you watching it pass by. It's the one universal speed limit. It never, ever changes. So think about it. If the light has to travel a longer distance, but its speed can't change, what's the only thing that can change? Time. It must take more time to cover that extra distance. So from your perspective, the moving clock's tick is longer. Time for that clock has actually slowed down.
Now, I know what you might be thinking. This sounds like a neat little brain teaser, a bit of a philosophical trick, but it's not. It is a physical reality that was proven, for real, in a brilliant experiment. Let's check it out.
So back in 1971, two scientists, Hefele and Keating, decided to test this. They took these incredibly precise atomic clocks, we're talking accurate to a billionth of a second, and put them on commercial airplanes. They flew them around the entire world, first eastward with the Earth's spin, and then westward against it, all while comparing them to a master clock they left behind on the ground.
Now, things got really interesting because two of Einstein's theories were kind of fighting each other here. First, his theory of special relativity said that because the planes were moving so fast, their clocks should tick slower. But then, his theory of general relativity said that because the planes were flying at a high altitude, where gravity is weaker, their clocks should actually tick faster. So the experiment was the ultimate showdown. Which effect would win, and would the results match Einstein's math? And when those planes landed, and they compared the clocks, well, the results were just astonishing. I mean, look at this. Just focus on the last two columns. The net predicted gain or loss was what Einstein's math said should happen, and the measured gain or loss was what actually happened. They were almost identical. His theories weren't just theories. They worked perfectly in the real world. So what did they find? The clocks flying eastward, which were moving faster relative to the center of the Earth, actually lost 59 nanoseconds. They were literally younger than the clock on the ground. And the clocks flying westward, moving slower, gained 273 nanoseconds. There it was, hard proof, time dilation is absolutely real. Okay, so time is flexible. It can stretch, it can shrink. But so what? What does that actually mean for us in our daily lives? Well, for one, it protects reality from breaking, and for another, it's the reason the map on your phone actually works. Let's look at how this whole time dilation thing prevents the universe from becoming complete nonsense. Imagine a space race to the nearest star, Alpha Centauri. Let's say the American ship leaves first, chugging along at 60% of the speed of light. Meanwhile, the Russians wait 4 years, but in that time, they build this hypothetical, souped-up ship, the Tachyon Terror, that can travel at 3 times the speed of light. They take off, easily overtake the Americans, and win the race.
Now, from our perspective back on Earth, this seems totally fine. They just have better technology. No big deal.
But here's where it gets crazy. Because of relativity, from the American ship's point of view, something completely impossible would happen. They would watch the Russian ship arrive at Alpha Centauri first, then fly backwards through space and time, and land back on Earth before it had even launched. I mean, that completely breaks reality. You can't have an effect happen before its cause.
And that's the key takeaway. Time dilation isn't just a quirky side effect, it's a fundamental rule of the universe. It acts like a cosmic speed limit, ensuring that nothing with mass can travel faster than light, which keeps the universe logical and prevents these kinds of impossible paradoxes.
Okay, but what about the here and now? This isn't just theory for spaceships. It affects you, personally, every single day. Just look at this number, 38,000.
That is how many nanoseconds the clocks on our GPS satellites gain every single day compared to clocks down here on the ground. Just like the airplanes, their clocks run a little faster because of weaker gravity, but a little slower because of their high speed. The net result? They get ahead by 38,000 nanoseconds a day.
Now that might sound like a tiny amount of time, but it adds up fast. If the engineers didn't constantly correct for this time dilation, your phone's GPS would be inaccurate by about 6 miles after just one day. The tech in your pocket only works because we account for Einstein's century-old insight about the nature of time.
And really, that's the big idea to take away from all this. Time isn't some rigid, universal metronome ticking the same for everyone. It's a stretchy, flexible part of the very fabric of space-time. Which leaves us with one last big question. If something as fundamental as time can bend and warp, what else about our perception of reality might be totally different from what it seems?